Hi, I'm Chris Kanich, and this is CS361, Systems Programming. Today, we're going to be talking about how best effort delivery, which is the delivery model for the entire internet, can actually be used to build reliable transport. And the TLDR, spoiler alert right here, the answer is that we all cooperate just like our kindergarten teachers taught us to. So to take a quick step back and define exactly what it is we're going to be talking about in this lecture, let's look back at our definition of the internet. The internet is a network of networks that delivers messages using a best effort packet switch delivery mechanism. So remember that the definition of best effort is that in our store and forward network, where we have a buffer, we have an input, and we have an output, we're going to be receiving messages as fast as we can receive them. We're going to store them into our buffer until our buffer fills up, and we're going to send them out the other end as fast as we send them out. If we're getting more in than our buffer or our output link can handle, we just drop them on the floor and we don't tell anybody about it, and the responsibility of resending those messages goes back to the original hosts. So why is best effort so much of a problem? Most of the time, silently dropping packets probably isn't what we wanted. If I sent you a message, there's probably a really good reason for me to do that, and I probably really want you to actually receive it. So we need to take the fact that this is how things work and know that everybody else in the entire world is also trying to do the same thing and say, how are we supposed to figure out how fast we're supposed to send at any given moment? So just a few more clarifications before we go through and directly answer that question. Let's figure out exactly what best effort service means in this context. So this basically means that routers must only accept packets, they must only advertise to everyone else, that the list of hosts that they can actually deliver packets toward, it's not best effort service for people to say, oh, hey, I can get you to Comcast or Google or Microsoft or whatever, if they can't actually deliver those packets for you. Just because they say they're willing to try, if they don't know that it's possible, it's not best effort service. Likewise, as I said on the previous slide, routers are expected to drop messages when their buffer is full. That's one of the main tenets of best effort delivery. And one thing that a lot of students ask about is where exactly network neutrality fits into this. And the most precise definition I can use is the one on the slide right here, where individual networks can't give priority to a given message based on its content. It can't say, oh, this is coming from a streaming service, I'm going to slow it down compared to the other things that you use your network connection to do, like email or browse the web. That's something that I would imagine Comcast probably wants to do to preserve the profit that they get from cable television. But with the way that network neutrality rules are written, if those rules are in effect, then they would not be allowed to do that. So other things that best effort service is not, that it doesn't require that you treat every single message the same. It's okay to sell one version of service to one user and one version of service to another, or even one priority level to one user, one priority level to another user. That has to do with ISP's relationship with their customer and not their relationship with the packets flowing through their network. Most of this type of thing has to do with packets flowing through a network rather than to a network, as you would see in a situation like you have Comcast as your provider. And another important part to this is that the entire system is voluntary, but that counts at a technical level, but it doesn't really have much strong meaning in a real world level. Right? So if I'm an ISP and I say, I'm going to make the best effort I can to deliver your packets, and then I have like a 56K modem sending all of those messages, then either you're not going to pay for that service in the first place, or you're going to realize that you paid for something that was wildly out of whack with what I'm actually trying to do to deliver your messages, and you're just going to take your business someplace else. This is a little bit tricky when ISPs are monopolies, especially for a lot of last mile connections, but it still is a reality of the way the network works. The technical protocols aren't going to cause you to get kicked off of the internet immediately when you don't do best effort forwarding, but in a competitive market, you would probably lose customers pretty gosh darn fast. So getting back to the challenge of store and forward, the idea here is that everybody obviously presumably wants to send their messages as fast as they possibly can and get them delivered as soon as they possibly can. So this causes a problem because everybody wants to do that, and there will eventually be bottleneck links within the network, right? So if we have lots and lots of different hosts and they're all connected to each other via some set of links, Some of them are going to be very, very fast, and some of them are going to be very, very slow. But eventually there's going to be some link that is the bottleneck, where lots of people are trying to send messages through this way. And lots of people are trying to send messages from here. And lots of people are trying to send messages from here. And eventually there's going to be way more messages going through than you have capacity to get them sent out towards that next router in the path. And so one of the first kind of really intriguing aspects of this portion of the module comes into play. So we can actually look at this through the idea of game theory. Give a really, really quick overview of what this is. The basic idea behind game theory is that when you have different entities that are kind of in competition with each other, they are going to have some strategy of how they're going to win the game. And based on, I don't win the game based on my own strategy alone. I win the game based on whether other people also do different things within their own strategy to win the game. So the two options that I have, so if I'm user A and you're user B, I can either go as fast as possible, or I can slow down voluntarily. And B can also do the same thing. They can choose, do I want to go as fast as possible, or do I want to slow down voluntarily when I see that there are too many other people sending at the same time? So they also have a set of decisions that they can make. They can go as fast as possible, or they can slow down. And now the first thing here is that if we look at the benefit to A and the benefit to B, if they both go as fast as they possibly can, they're both going to be pushing as many messages as they possibly can through that bottleneck link. What will likely end up happening is that a lot of those messages do get dropped. And just because we're talking about 2 users doesn't mean we're not talking about a lot more users. When there's 2 users, maybe if they both push as many as they possibly can through that same pipe, they'll cause a lot of dropping, and they're going to congest the entire network, because every single time something gets dropped here, that means that even though it was sent here successfully and sent here successfully and sent here successfully, I have to go back through and send it again through here, and send it again through here, and send it again through here. So even if those links weren't congested, they're going to get a lot more traffic than they would have otherwise. So that's a bad thing. And if you generalize this out to lots of users, the success rate of getting through a bottleneck link when 5 or 6 or 7 users are trying as hard as they can to get as many messages through, what you end up with is that the utility, like how many messages you're going to get through per unit time, is going to be effectively equal to 0 for both of them. If I go as fast as possible and you go as fast as possible. If I slow down and you keep going fast, A is going to have effectively 0 throughput, and B is going to have n throughput, where n is the full bit rate of that bottleneck link. They're going to be the one that gets all of these messages sent through, but it's probably going to be less than n. Now that I think about it, it's probably going to be, a little bit less than n, because if they send so many messages, they themselves are going to fill that buffer, and some of the messages that successfully got through all the way to that bottleneck link are going to be dropped. So they're not even going to get n, because they're causing their own messages to get dropped in the network after they've gotten all the way to that bottleneck link. Likewise, it's symmetrical. A will have some value that's slightly less than n, and B will have effectively equal to 0. Then we get to that last square down here, where both of us voluntarily slow down. The reality that we end up with here is that if we both slow down when we see that the buffer is almost full voluntarily, then we're both going to get about half of the whole bandwidth available on that network link, which is pretty awesome. That's more or less optimal for us. If we both send at a certain rate and then say, oh, nothing got dropped, then we send a little bit faster and say, oh, nothing got dropped, then we send a little bit faster and say, oh, nothing got dropped. If we keep slowly increasing our speed until we see that a message has been dropped and then slow way down, we can actually coordinate with everyone else that's following the same set of rules. So if everybody keeps following these rules, then everybody gets an equal share of the bandwidth. If some people start trying to hog that bandwidth, then almost everybody is going to start getting worse service, And if you get worse service because somebody else is trying to hog it, you say, well, I want to get some messages through, so I better try and hog it too. And immediately, any strategy that looks like that leads to this thing called congestion collapse, where the entire network doesn't give any good throughput because it's just dropping so many messages throughout the entire network, and almost nothing can get through successfully. The latency spikes way, way, way high. The throughput goes way, way, way down to effectively zero. And this kind of incentivizes everybody to play well with each other, because as soon as we stop doing that, the entire thing falls apart. So what this tells us is that A, it's possible to voluntarily get everybody to agree on how fast they should go and whether they should slow down, even though they all presumably want to use the network as fast as possible. And we can do this in a distributed fashion where each individual user doesn't have to coordinate with each other. They all just take this signal of a message being dropped, and they take that as a signal, hey, I sent faster than the network can handle. I'd better slow down for a while to allow those buffers to clear. On top of this concept, we still need to build a mechanism to provide reliable byte streams. And that's what TCP is, if you've heard of that. The Transmission Control Protocol is the reliable in-order byte stream mechanism that will provide a lot more features, including congestion control, although congestion control is kind of like the coolest aspect of it. So in addition to that, TCP will also split these byte streams up into individual messages so that when I say do a send from a buffer of 10,000 bytes, the messages that go through the internet are not actually 10,000 bytes. They're either 9,000 or 1,500 in most situations, or sometimes a little bit less due to some tunneling. So if I tell the operating system, hey, I want to send 10,000 bytes, one of the things that TCP will do is it will split that up into 1,460 byte packets in the most common case, put a little TCP header on them, put a little IP header on them, put a little Ethernet, if that's the network they're on, header on them, bring them up to 1,500 bytes, which is the maximum transfer unit for Ethernet, and send them all one at a time through the network. And then if any one of those messages gets dropped, it will have a timer saying, hey, I didn't get any message back saying that this was delivered successfully, and I better resend it. And this is all to say, and I'm getting ahead of myself a little bit here, because another big thing that TCP does is it sends acknowledgements. So for every byte of data that goes through the network, there will be an acknowledgement packet that acknowledges that that byte has been delivered. So typically you don't acknowledge every single byte within that entire message. You just acknowledge the last one, saying, I've heard every single byte up to this number. And so as soon as any of these messages get over to their destination, the destination will send an ACK back, an acknowledgement, usually called an ACK, that says, hey, I got that message. And then, hey, I got that message. Hey, I got that message. And so what TCP will do is it will say, okay, I know the last time I sent a message was at this time, and I got the ACK back at that time. Take the difference between those two, add a little bit of extra slack on the end, and it sets a timer saying, okay, I'm going to send this next message. And if I don't get a response back in that much time, I'm going to assume that the message was dropped. So the two important things we need to do are A, slow down and not send as fast because we probably caused congestion, and B, resend that message. So we resend those messages when they get dropped. And as I mentioned on this slide and before, we're also going to be slowing down when we detect that congestion, and we detect congestion based on the presence of dropped messages. There are some more advanced versions of TCP that are in use today that use the amount of latency on a returned successful packet to figure out when congestion is happening, but most of the deployed TCPs that we use today use dropped messages as a signal for congestion. So we motivated this entire conversation about best effort delivery and reliable transport based on that one bottleneck link, right? Where we have one router connected to another router, connected to another router, and we have this bottleneck link that's like 10 Mbps or something. And then we go through the network all the way to our destination. So one kind of tricky thing that the hosts at the end can't do is they don't see that 10 megabit link. They don't know that there's some 10 megabit link in the path between the source and the destination. From the point of view of those end hosts, this is all just a completely opaque cloud that they just send messages into. They have no idea what the rates are or the buffer sizes or anything that's happening in there. But what they do know is that if a message gets dropped, the most likely reason is that they filled up a buffer someplace. So what will end up happening is each of these routers is going to have a buffer. What will end up happening is that we've done two things when we cause a congestion-based packet drop. One is we've sent faster than the bottleneck link. But two, this is really, really important, we filled to the brim that router's buffer and probably some of the routers before that one within this entire path and maybe some of the ones after it. But this is the one that really matters. This is where the packet got dropped and caused the lack of an acknowledgement to come back. So what this actually means is that if we graph over time and we have our congestion window, which is basically how fast we allow ourselves to send, over time we're going to be going up and we're going to be going up. We're going to be slowly going faster until we see a drop happen. Now, if a drop happens right here, I have one of two options, and kind of theoretically, if we think about this. I can either say, hey, I dropped, I'd better go with the same speed here. Or I could say, hey, maybe, hey, I dropped one, and so maybe I need to slow down just a little bit. Or a last option is to say, hey, I should probably slow down a whole lot and then slowly work my way back up again. So one of these things is not like the other. That's probably the correct one, and you would be right. What we do in reality is not either of these things. We continually go way, way, way down and then slowly work our way back up every single time we see a congestion drop. And this is because once we get up here and we see an overflow, that doesn't just mean we went faster than the bottleneck speed. We probably went faster than the bottleneck speed for a really long time because this router was sending messages, was draining its buffer as fast as it possibly could while we were filling it up. So what we need to do is we need to slow way, way down like here. As we send down here, we're sending slower than that bottleneck link, and that bottleneck link can actually drain its buffer back down to a healthier level. One other really useful benefit to this is that if we are constantly going a little bit faster than slowing down, going a little bit faster than slowing down, then we'll be able to quickly react to changes in how much bandwidth is available. Because say, for instance, somebody was sending a really, really long, really huge file, then all of a sudden at this time, they stopped sending it. Well, then I'm going to be continually going faster and continually going faster. And then instead of having to slow down here, maybe I can just keep going faster and faster and faster. Eventually, I'm going to have to come down and then work my way back up again. But because I'm constantly probing for more bandwidth and slowing down and kind of waiting for all of my probes to drain out of the network before I start over again, this allows me to react to changes in the network. And they can react both on the way up, like so, or, for instance, if somebody else started using the network and we all needed to share it, maybe I would slow down faster because someone else was also filling that buffer and the buffer fills faster, and I've got to slow even further down. By doing this, so if we reach some sort of steady state, even when nobody else is using the network, a typical TCP implementation like this will send in this sawtooth pattern. And the bottleneck bandwidth is probably somewhere around here, but we're going to just bounce around it in order to, A, drain the buffers in between the source and the destination, because when we cause congestion, that means that not only did we go faster, but we also filled the buffer. And B, we're going to always be probing for more bandwidth so that we can figure out whether we should go slower or go faster based on the conditions of the network. So this isn't as important to the concept of best effort or congestion control or any of those things, but other features of the transport layer that are pretty important here are port numbers, which we use to multiplex for processes. So whenever I'm drawing these diagrams with hosts and routers, I'm usually drawing them where each individual element is a computer. Now, when we have end-to-end connections between a source and a destination, it's not this computer that wants to talk to that computer. That's not a thing that computers do, right? The computer is just a way to run lots of different processes. And all of those processes are going to have the same IP address because they all live on the same host. And some of these processes are probably going to want to make more than one connection. They're going to want to connect to different places and to different services. And so this is where we're going to use the idea of multiplexing through the use of a port number so that we allow individual processes to talk to individual other processes. So each individual, say, TCP conversation is going to be uniquely defined by the source IP, the destination IP, the source port, and the destination port. This is sometimes called the TCP4 tuple. So an individual connection will have this unique identifier, and the operating system will be multiplexing between different socket file descriptors based on reading out the source IP, destination IP, source port, destination port. We're going to learn a little bit more about what we use ports for in the client-server model a little bit later on, but this is another really important part of what the transport layer provides for us. Another important thing here that I mentioned in a previous video is that we don't always want to have perfectly reliable in-order byte streams. Sometimes we'd rather receive a message as fast as possible rather than wait for a message to be retransmitted. This can be because the messages are really small. This could be because we care more about the latency than we care about the accuracy, the error rate of the delivery. And if we want to provide services like that, we use the user datagram protocol, which provides unreliable service for individual chunks of messages. Another really interesting thing that UDP gets used for is if I want to create a completely different reliable transport mechanism, I can build it on top of UDP, because UDP is kind of like the tiniest little layer of extra functionality on top of the raw best effort service that's provided by the Internet Protocol. In addition to that, especially in TCP, there's rules about how these connections get initiated and synchronized, because this is a distributed algorithm running between two hosts that can't otherwise talk to each other. So they need to kind of sync with each other to make sure that they're on the same page with respect to who's talking when and where and how, stuff like that. That's all I have for you on best effort service. Hope you enjoyed this lecture, and I'll see you next time.